This is Chapter 6, Problem 47. Here we have the dreaded Ferris wheel problem. You will have a mass of 80 kilograms going around a Ferris wheel with a radius of 10 meters and a velocity of 6.1 meters per second. We can find the period of one complete revolution by taking the circumference, 2 pi r, and dividing by the velocity. Think of distance over time. So the total distance traveled in one complete revolution is the circumference, divide by the velocity. You should get a period of about 10.3 seconds. So that part's easy. Now we're trying to figure out the normal force at the top and bottom of the Ferris wheel. Here's where the free body diagram is hugely important. At the top and bottom, the free body diagram for a person sitting in the Ferris wheel looks pretty much the same. You have the normal force acting up and mg acting down. However, at the top of the Ferris wheel, the centripetal force is pointing down. That's because it must always be pointing towards the center of the circle. The centripetal force is equal to our net force, so F net is equal to minus the centripetal force, since the centripetal force is pointing down. That means that when we add up all of our forces, the centripetal force, with a negative sign, it's pointing down, must be equal to the normal force minus the weight, mg. Solving for the normal force, we get that the normal force is equal to mg minus fc. So at the top, you are going to feel between your butt and the seat a little bit less force than the force of gravity. Think about going on a roller coaster. At the top, you kind of come out of your seat a little bit. Think about that. Solving for the normal force, we have the mass, 80 kilograms times 9.8 meters per second squared, minus the centripetal force, which is mass multiplied by the velocity squared, divided by the radius, 10 meters. And we get a normal force at the top equal to 486.32 newtons, which again is less than the weight of the person if they were just at rest on the ground. Now we're going to set up the free body diagram at the bottom of the Ferris wheel. And at the bottom, again, we still have the normal force pointing up, the force of gravity, mg, pointing down. Only now, since we're at the bottom of the Ferris wheel, the centripetal force is pointing up. So now the net force is equal to positive Fc, and that means that the centripetal force is equal to the normal force minus mg, and the normal force is equal to Fc plus mg. So just take your work from before, and now you add the centripetal force to the weight of the person, and you should get a normal force of about 1100 newtons. It's 1081 newtons, which means that at the bottom of the Ferris wheel, you're going to experience more force than you would at the top.